We now come to our next rapid fire speaker, Morven McLean. She's the Executive Director at the International Life Sciences Institute Research Foundation. And she'll talk to us about the next generation of genetically engineered crops. What can we do differently? So yet another take on the question. Thank you very much.
Thank you very much. So thank you very much, Claudia, for inviting me to join you here. So plant breeding has historically focused on yield improvements, both directly, for example, through more grain per head, more fruit per plant, and also indirectly by conferring tolerance or resistance to biotic and abiotic stressors that reduce harvestable and marketable yields. Increasing yields has an obvious positive impact on food security. However, we also know that increasing calories alone is not sufficient for ensuring healthy development. Meeting caloric intake requirements does not mean that nutritional needs are being met. This is well understood, and it's why there's significantly more attention being paid to nutrition-sensitive agriculture now than, let's say, 20 years ago. Advanced plant breeding techniques have a role in contributing to improved yields and improved nutritional content of our staple food crops. And that includes applications of genetic engineering and gene editing. So I'm going to focus on this topic since it's how I first came to meet Mark over 12 years ago when we started collaborating under the USAID-funded South Asia Biosafety Program. I've learned a lot about agricultural policy from Mark over our time working together, and I'm incredibly fortunate and grateful to have done so. Genetic engineering isn't just GMOs. It's an invaluable research tool that's helped advance fundamental understanding in plant development. This basic research has been translated into knowledge that's used to develop new plant varieties or hybrids with improved traits, using conventional as well as more advanced plant breeding approaches. But when looking at the application of genetic engineering in agricultural production systems, front of mind are genetically engineered plants, specifically maize, canola, cotton, and soybean expressing the traits of herbicide tolerance and/or insect resistance. These are the predominant GE plant trait combinations that are currently cultivated across the world today. But when we look at research and development taking place around the world, the pipeline is significantly richer. For example, in a 2014 survey we did of 320 public and private sector organizations working in agricultural biotechnology, plant biotechnology specifically in India, we found that over 85 different plant species were being used in experimental work, including plants used for food, for livestock feed, for fiber, for fuel, for dietary and medicinal purposes. There was significant research on traits that are relevant to mitigating the impacts of climate change, such as tolerances to drought, to salt, and to heavy metals, and in crops that are important for smallholder farmers, like millets and pulses, that may be increasingly important for addressing food and nutrition security. But what the survey also showed was that most of this research was early phase, and to date, with only 20% progressing through to confined field trials, not even through to commercialization. Overwhelmingly, the deterrents to pushing through to commercialization were the cost of meeting regulatory requirements and a political environment that was generally considered to be hostile to the technology. And this is a situation that we see replicated in many countries around the world. So enter gene editing. This is a more refined approach to making specific directed changes in the plant genome and can be used to make novel plants that might not be considered GMOs in the more traditional sense. This kind of targeted breeding, in combination with high throughput phenotyping, can reduce the cycle time to achieving desired characteristics in the crops that we want to focus on. This is important for at least two reasons. First, breeding of many of our important crop species is a long game, especially for perennials, but even for some annual crops, particularly those that haven't been the focus of aggressive breeding efforts in the way that rice, wheat, and maize have been. An accelerated change in production systems so that the specific target of a breeding program may end up being eclipsed by a new pest or pathogen complex or some other production constraint that was not even anticipated in terms of its economic impact at the start of the breeding program. So there's a lot that can be learned from the last 20 years or so of how conventional transgenics, if we can call them that, have been managed, and how economic, social, and political drivers have affected their regulation, their deployment, and their adoption around the world significantly more than the science has. Gene editing is another transformative technology that's going to have an impact on the food that we eat and how we grow it. As Mark pointed out in his book, Food Security in a World of Natural Resource Scarcity, different regions require different technologies to respond to or adapt to the pressures of climate change, and combining multiple technologies can have an even greater impact. Perhaps the focus this time around should not be on the technology per se, as was the case with genetically engineered plants, but instead on what the gene-edited products can contribute to both yield and nutrition gains when stacked with other technologies and appropriate management practices. So let's look at the whole package and not just on one of the ingredients. Thank you.
Wow, I think that was an excellent speech and a very nice summary on what we really should be doing differently and how to move forward.